Alright, this is the last video on Boolean algebra. It's going to cover D-type flip-flops, half, and full adders. Let's just get straight into it. So before we can fully talk about what the D-type flip-flop is, we need to first talk about the SR latch, which is a component of the D flip-flop. So let's try and break this name down. The SR part just means set reset, and the latch is a logic circuit used to store a single bit of data. And a property of latches are that they update as soon as the input changes. So before we get into any of the logic, the SR latch just basically takes two inputs and has two outputs, Q and not Q. And what I mean by storing a single bit of data is that if you look at the outputs, we have Q and not Q. So if we wanted to store a 1, then we would have Q as on, but then not Q would obviously just be the opposite of Q. So not Q would be 0. And if we wanted to store a 0, then Q would be false, which means that not Q would be true. So let's get into the actual circuit. You can see it has two NOR gates, which is basically just an OR gate negated. And I'll give you the truth table of a NOR gate. So let's just try some inputs. Let's say they're both 0. And these are zeros by default. Then if we look at the truth table for a NOR gate, you can see that if both inputs are zeros, then it outputs a 1. So in this case, both gates should output a 1. But if we look at where their outputs are linked towards, they're actually linked towards the other gate's input. So let's say if this was the top one, outputted a 1, then this bottom one would change to a 1, and then this would output a 0. So in reality, they can't both output 1 at the same time, because, well, these are actual logic circuits, right? In reality, one is going to output theirs first, which means that takes the first output. So really, it doesn't matter which one has the output of 1. Let's just say the top one has an output of 1. So if that's the case, then the logic circuit would look something like this, right? So now let's think about what these inputs actually do. If we have the set button as 1, this 1 and 1 make the gate continue to output a 0, which means nothing changes. But let's say instead we wanted to input a 1 into the reset input. Well, that would make this a 0, and then you can see how this is linked to the input of this gate, so this is going to be a 0. But then this turns into a 1, right? Because NOR gates, if both of their inputs are zeros, then the output 1. Which means that not Q now becomes true, and then this becomes a 1, which it continues to output a 0. And now, if we wanted to set it, we change this into a 1. This becomes 0. This is going to be off as well. This will be 0, and then this is going to be a 1. And this is also 1. So you can see how setting, if we have an input in the set input, then that gives an output of true for Q. A reset input would give, would just turn Q off and turn not Q on. So you can see how they sort of store a single bit of data. Now let's talk about the D latch. So the D latch has the SR latch part of it, but it also has this new part, right? And it has one input, D, and it has an enable. And what the D latch does is that it effectively has the same purpose as the SR latch, but in this case you only have one input, which is D. This enable sort of acts like an input, but we don't count it as one. The basic explanation of how a D latch works is that if this enable is on, then once you have an input of 1 for the D input, then Q is stored with a 1. and not Q is just the opposite of Q. If D becomes a 0, then Q will be 0 and not Q will be 1. And the purpose of this enable is that as long as the enable is on, then you can change the state of the latch. But if the enable is not on, let's say the enable gives a 0, then these two AND gates will always give an output of 0. So nothing on this SR latch side does anything. So you can only change state when the enable is on. Now, before we talk about the D flip-flop, we need to first describe the difference between a latch and a flip-flop. So latches are level sensitive, which means it continuously monitors its inputs and changes its output whenever there's a change to the input. Flip-flops, on the other hand, are edge-triggered, meaning it captures data as specific clock signal, and there's a fixed time period depending on the clock frequency. We'll get into this clock part when we get to the flip-flop, but just know that there's a difference between latches and flip-flops. So here's the circuit for the D flip-flop. You can see it's basically the same as the D latch, but instead we have a clock here. And so what this clock is, well, it's basically just a pulse. With a fixed time period, it gives a 1, and then it goes back down to 0, and then within that time, the same time, it goes back to 1, and it repeats this. And so, well, what does this mean? It means that you can only change the state of the D flip-flop whenever this clock has an output of 1. And so, well, what's really the benefit of this over the enable from the D latch? Well, you may prefer the flip-flop over the latch because oftentimes inputs come in at random, and the clock ensures the output is synchronized with the entire computer system. The basic idea is that your computer system is very complex, right? And sometimes you want to store data, and other times you don't. If you use the enable, well then it's going to get quite complex, right? Because you're going to have the enable on for each of your D flip-flops, and these flip-flops only store 1 bit of data. So imagine if you have like 64 gigabytes of data that you need to store, you're going to need an enable for each of those, right? And that gets very complicated, right? Because how are you going to manage all of those enables? With this, a clock is much more simpler and ensures that things are synchronized, which is good. Now let's talk about half adders. So what's the purpose of a half adder? Well, it's just a logic circuit that's used for binary addition. It's designed to add 2 binary digits, which are basically just bits, and it has 2 inputs and 2 outputs. The 2 inputs are either 0, 0, 0, 1, 1, 0, and 1, 1. And these just represent all the possible different bits that you can add up, right? If you think back to binary addition, let's say you're trying to add 2 bits, right? Well, 0 and 0. The sum of this is 0, and what you carry over is 0. If you're trying to add 0, 1, the sum of this is 1, and what you carry over is 0. If you're trying to add 1 and 1, the sum of this is 0, and you carry over a 1 to the next place value, I guess. You also need to know about the logic circuit. So this is what the logic circuit looks like. It uses an exclusive OR gate and an AND gate. Now let's talk about the full adder. So the full adder is basically just a better version of a half adder. With the half adder, you only add 2 inputs. But with this one, it's designed to add 2 binary digits, but also accounts for a carry as an input. So there are 3 inputs and 2 outputs. Regarding the 3 inputs, one of them is a carry, and the 2 other inputs are the same as the half adder. So imagine you're adding 2 binary digits, let's say 0 and 1. But in this case, there's a carryover from whatever you were adding up before, right? The sum of this is going to be 0, and you carry out a 1. The truth table for this looks something like this. So you have 3 inputs, A, B, and the carry-in. This truth table shows all the possible inputs you can have when you add two binary digits, right? You can either add 0, 0 and have a carry in of 0, 0, 0 and have a carry in of 1, and so on, right? It shows all the possible outcomes. And if we look at the circuit of a full adder, you can see it has two half adders in them. A third input, which is the carry in, and these two half adders are joined together with an OR gate. And you need to know this circuit for your exams. And that's basically it for this video and this whole topic. I did feel like I kind of rushed through it, but yeah, I think I went through all that you need to know. Maybe there's some like small stuff that I didn't go over, but you can have fun learning that.